Um, the idea of reduced order modeling is that a lot of physics simulation data or experimented data are in some high dimensional space, okay? And then because of the dimensionality, computationally it's very expensive, and also you may actually miss a lot of important trend by looking at only those high resolution small local regions. So the idea of reduced order modeling is to reduce the dimensionality of the problem and then learn the physics over there. So here are some examples, right, of energetic materials. So kind of continuing from the yesterday's example, we have some microscopic structures, and then the shock is applied from the left to right, and then the collapse of this, pore will result in the formation of the hot spots. And then, you can see on the right, we have the shock front sort of, deflected and, gets coupled with the other, traveling shock. And then we get to have this kind of really violent dynamics. Now, the idea of reduced order modeling is that, so in this case, we have, in terms of the dimensionality of this, this problem, we have this, pixel space, okay? This pixel space is discretizing the actual physical space. And that pixel space, for each of the pixels, we have essentially two values, one for temperature, one for pressure, right? So in terms of the dimensionality of the problem, the Banach space is defined as W by H by 2 tensor. So we have some, number of pixels, W in the width direction. And then we have some number of pixels in the height direction. And then for each of the pixel, we have a temperature and pressure. So it's total W by H by 2. Of course, the space would be an infinite dimensional space, right? Because we were talking about a continuous domain. But, after discretization, we have WH by 2 as our, size of the Banach space. And then in that W by H by 2 dimensional space, some, physics, right, is evolving. So the values in that W by H by 2 space will evolve over time according to some dynamics. But then if you think about it, if you have some high resolution data, the W by H is going to be some large number, right? So if you have, let's say, yeah, if you have, let's say, 100 pixels in the height direction and the 100 pixels in the width direction, that's total of 10,000 pixels, right? Which is already a lot. So the space of dynamics is going to be 20,000 pixels. And then if you go even a higher dimension, then the dimensionality of the problem is going to grow really quick. So the idea of reduced order modeling is to reduce the dimensionality of your problem into some space, okay? And then instead of learning the dynamics in the original high dimensional space, we project all this, interesting dynamics onto the lower dimensional space and then learn the physics there. So the Rn, okay, where n is essentially the original high dimension. So in the previous case, we have W by H by 2. So W times H times 2 is what is defined as our dimension n, right? And in that n-dimensional space, the assumption here is that only a thin subspace, okay, of that Rn is the space where the interesting physics happens. And then as you go off of that thin subspace, okay, we get temperature and pressure configurations that are not realistic, okay? So if you think about it, if I arbitrarily assign numbers for the temperature field, then likely I'll get some, weird configuration of temperature that can never exist in the physical world, even though, mathematically I can just assign some random numbers here, right? But as a result of that, we'll have almost like a TV static, right? Where the pixel values are all just randomly distributed, right? And that will never look like a real, physical phenomenon. So if you think about it, only very particular combination of pixel values are the ones that are considered to be physically realistic snapshot. And then everything else is going to look like, TV static or something unrealistic. So with that in mind, this entire space of Rn is going to be likely filled with some random combination of pixel values. And only a small subset, okay, of that space will correspond to the actual physics. So that's this green surface, okay? And, in terms of the terminology, we're going to call it an invariant manifold or the dynamics manifold, okay? And on that dynamics manifold, we assume that there's some interesting dynamics that's happening, okay, which is denoted as a trajectory or a curve on that manifold, okay. So this particular over here is what corresponds to, one simulation. And then on that invariant manifold, there can be many different trajectories corresponding to different, boundary conditions, different initial conditions, different physical parameters, and so on and so forth. So that's the problem setting. Now, the idea of reduced order modeling is that since, our view is that only the thin subset of the original n-dimensional space is really where the physics happens, we do not need the entire n dimension, okay? This subset may be some much lower dimension m, okay? And therefore, if we can somehow learn this m-dimensional space, okay, and how this m-dimensional invariant manifold look like, then instead of dealing with the dynamics in the original n-dimensional space, we should be able to go down to a much lower dimension m and then represent the dynamics over there, is the idea of reduced order modeling. Does that make sense? Yeah. So at the end of the day, it sort of boils down to the problem of creating a map or a cartographic map. So, the Earth's surface, okay, is a two-dimensional surface embedded in a three-dimensional space. So the universe, right, that we're living in, if we ignore time, is three-dimension, right? And in that three-dimensional space, we have a sphere. And if we're only interested in the surface of the sphere, then the sphere itself is 2D, right? And we would like to do is to create a representation of that two-dimensional manifold onto a flat piece of paper. So that's the whole idea of a map, right? And obviously for spheres, there's no way we can make it completely flat. So all the maps that we see are somehow distorted. And then of course there's a discontinuity as well. So we basically split the sphere into half and then unfold the sphere to create a flat map. But once we have the map, okay, once we have the map, we no longer have to think about the sphere. We can do pretty much everything on that flat piece of map. For example, when I make a plan, I don't need the actual sphere or a globe, but I can just look at the flat piece of paper and then plan for my destination, how I'm gonna travel. On your phone, you guys have all, Google Map or some sort of a digital map, right? Again, when you travel from one location to the other location, you don't really consider that spherical geometry in mind. You take a look at the, two-dimensional map, and then you can pretty much do everything, right? At two-dimensional map, we have the coordinate system, longitude and latitude, right? And longitude and latitude is a coordinate system that assign a, unique coordinate values on every location on the Earth, right? So in that way, we can pinpoint the location using the two numbers, longitude and latitude, right? And pretty much cover the entire sphere, right? So same thing. What we're gonna do is we have this likely curved m-dimensional space. Okay? We don't actually know if it is really curved or not because the n dimension n is really high, and then even if the lower dimension, reduced dimension m, is relatively small, still is beyond the dimension that we can visualize. So we cannot really know if the invariant manifold is actually curved or not, but there are some ways to measure that. But nonetheless, we're going to assume some generic curved geometry, and then from there we would like to create a map. Okay, we would like to create a map of that invariant manifold, and on that map we're going to make our travel plans. Okay, so even if, because the Earth is curved, even if our trajectory, the actual trajectory of our trip is going to be curved, right? On the map we have a flat piece of paper, and then we can represent the trajectory exactly on that two-dimensional map. So what we're interested in is to, first of all, produce the map. And then on top of that map, we would like to define a governing equation governing those different trajectories. Does that make sense? Yeah. Now, speaking of the map generation, maps are not accurate. Okay. One of the things that in differential geometry, a curved space cannot be perfectly, represented on a flat space. Okay, this is a theorem called Gauss-Gray theorem. This is this is the only mathematical theorem that has the word great. Okay, so Gauss came up with this theorem that says, there's no way you can, make a curved surface perfectly flat. Okay, because what's called the Gauss curvature must be preserved. Okay, and what that means is, similar to drawing the word map. There's no way we can, create a map without inducing a distortion. So for example, the usual word map that we see every day is what's called a Mercator projection. So Mercator projection, we have a sphere, we draw, longitudinal lines and the, latitude lines, right? And then using them as the, perpendicular coordinate system, we, flatten the sphere onto a 2D piece of paper. But as a result of that, the countries near the equator are represented pretty accurately. But then the countries that are closer to the North Pole or the closer to the South Pole will be distorted. So the actual size of Russia is not that big, even though in the Mercator projection, Russia is gigantic. But in terms of the actual size, they're not as big as what is represented in the Mercator projection. Or Antarctica is like probably the biggest continent according to the Mercator projection, but that's not true because Antarctica is kind of stretched during the process of map making, and as a result of that, we have the delusion that Antarctica is a giant continent, when in reality it's much smaller than what it looks like. There are many different types of map projections. So there's a thing called the Robinson projection, and all kind of different projection methods, where people somehow try to reduce the distortion so that the countries are represented properly according to their size. But nonetheless, whatever you do, there's no way mathematically you can make a perfect map that preserves everything. So what that means, okay, in the process of generating maps, what's going to happen is the places on this map, on this invariant manifold, are going to be distorted, right? So some countries will be distorted and then make it look bigger on this map. Some countries will be distorted and get shrunken, right? And not only the area, but also the angle can be distorted. So let me actually. So historically, people have been, making a lot of different projection, a lot of different maps. So here's one way of creating map. Yeah, this notorious Mercator projection here. So this is the usual map that we have. Countries like India, closer to the equator, are relatively well represented, whereas places like Greenland, this is actually much smaller. Same thing with Russia. Russia looks very big, but in terms of the size, they're not that big compared to countries like China or the U.S. Canada also got distorted quite a bit, right? So in case of the Mercator projection, they preserve the angles. So what appears to be 90-degree on the sphere will still be 90 degrees in the Mercator projection. So the longitudinal line and the latitudinal line will cross at the right angle, right? And that angle is preserved in this particular projection. However, projections like this, okay, projections like this is called a transverse Mercator projection. So instead of stretching and crack opening the North Pole and the South Pole, we're actually crack opening the equator. So we're making the projection in the same way, but in a traversal direction is what's happening over here. So as a result of that, now the Antarctica over here is well represented, right? The size of Antarctica is represented correctly. And then now Canada is much smaller compared to the original Mercator projection. But then with this mapping, the angles are distorted. Okay. So what used to be a straight line is not a straight line anymore. You see what I mean? What used to be the longitudinal lines and the latitude lines, which are straight lines in the original Mercator projection, are now distorted. They're curved. Or here's some other silly projection here. And again, this one maybe preserve the area of the size of the country, the landmass more correctly, but the lines are all curvy, This is, I think, Robinson projection. Maybe I'm wrong, but looks like Robinson projection. So Robinson projection is another type of projection. And in this one, better preserve the landmass. But again, in the meantime, the angles are not preserved. So the longitudinal lines and the latitudinal lines, they're supposed to cross at a right angle. But then if you look at, for example, over here, we have some obtuse, angle that is much greater than 90 degrees, right? So, you have to give up one thing. If you preserve the distance or area, then you have to give up, the angles. If you preserve angles, then you have to give up the distance or area. Okay, and there's no way that you can preserve everything. Is kind of what Frederick Gauss has said in his theorem. Okay, so in terms of physics, what happens is during the reduced order modeling, when we generate a two-dimensional map, flat map of some curved manifold, there's going to be a distortion. Okay. And the distortion of distance and the distortion of angle is going to have a physical meaning. See what I mean? For example, velocity or relative velocity. Let's say in the original physics space, in the high dimensional space, let's say two cars were, driving at, 60 kilometers per hour and with the angle of, let's say, 30 degrees to each other. So that's the original physics. But then if you create a map with a distortion, then the angle between their velocity vector may not be 30 degrees anymore. And also the relative speed, I mean, the speed, that's the size of the vector may not be perfectly preserved. So even though they're actually driving at the same speed, depending on how you draw the map, one car may appear to be 10 kilometers per second, whereas the other car may appear to be 50 kilometers per second. And then the length of the arrow is going to be distorted accordingly. So not only so when you map the velocity vector, acceleration vector, all these physical quantities onto a flat space, then the vector will undergo some rotation and stretching, right? So that is, what's going to happen, which is why, when you draw a straight line on the Mercator projection, airline companies will, present their routes, right? And when you, see those kind of visualizations, airplanes seem to fly, along a curved path on the map, which on the sphere is actually a straight line, right? But because of the distortion, it appears to be that a flight that, departed from Washington, D.C. will go up for no reason and then come down again to get to India, right? But in reality, it's a straight line, right? It's just that the map is distorted. So we're basically learning the physics in that distorted space is what's happening. Okay. So there are several research questions. One is, how can we create a map by minimizing distortions? And because we cannot have distortion zero, we cannot make the distortion to be zero, we have to give up certain things. So what is more advantageous, for example, in learning the physics of fluid? Do we have to give up the angle? Do we have to give up the length? What do we have to give up, right? Is one of the research questions. So the map making itself is a research question itself. The second question is, even if we somehow minimize the distortion, there's still going to be distortion. So under the presence of distortion, now how can we model the physics in that distorted space? Okay. So if you go really deep into this, it's a very, very, sophisticated topic, which requires a differential geometry and, things like that. But today we are not, here to, go into that level of detail. But instead, I'm going to introduce some of the tools that are commonly used in reduced order modeling, especially the neural network tools. And then from there, we'll see some examples. Yes. In the original domain, you may or may not have a differential equation. Okay. And even if you have the differential equation in the original domain, in the reduced domain, the same equation may not be true anymore, right? Because the whole idea of differentials will be distorted. So the differential operators actually have to be transformed into some arbitrary shape. So almost always in reduced order modeling work, we somehow, disregard the governing equation. Even if you have the governing equation in the reduced space, that same equation will no longer hold true. So instead, you drop that equation, start from scratch. Of course, there are techniques to somehow translate the governing equation, and then that's actually one of the things that my group is working on, but it's not that easy. So again, this invariant manifold, the green curved surface, is essentially where the actual physics is happening. So if you collect all the physics trajectories, all the trajectories of the fluid, for example, then those trajectories will going to span this curved manifold. That is the Banach space. Yeah, a subset of the Banach space. This entire thing is a Banach space, and then we have a subset of the Banach space. Yeah, you can say that. Yeah, we call it the invariant manifold because this is where the dynamics is defined, and this is something that we would like to model, right? And this doesn't change, right? If there's a physics governing principle, that governing principle is going to determine this manifold, and we want to find that one. So that's why it's called the invariant manifold. And then this yellow thing is a map of that curved surface. True, true, true. Yeah. Depending on how accurately model that green manifold, like in this diagram, we're approximating this green curved space with this flat plane, right? And from that projection, obviously, there's going to be distortion. And then as you go to a certain place, because the distortion is too severe, the reduced physics will no longer capture the actual physics. Yeah. Yes. Yeah, so that's the whole point. That's essentially what we're gonna do. Yeah, we want to find the best representation of this curved space, somehow using neural networks. All right, so this is where we introduce what's called the autoencoder. Autoencoder is essentially a multi-layer perceptron. Okay, it's a multi-layer perceptron that looks like an identity function. So what that means is to this neural network, we have inputs x1 through some xn. That goes in as an input, and then the neural network will spit out the exact same output. So then what's the point? Right? The same input goes in, the same input comes out as an output. What's the point of this silly neural network, right? The thing is, we have this dimensional bottleneck. So the way we define the autoencoders is we have an MLP, but the hidden dimension should be significantly smaller than the input dimension. Okay, so some n-dimensional input comes in, and that same input should be reconstructed as an output. But in the middle, we have only D neurons, where D is significantly smaller than N. And the neural network is forced to learn to compress this original n-dimensional input into some d-dimensional encoding, so that from that d-dimensional encoding, you can reconstruct the original information. Okay. And therefore, by training this specific type of MLP on some, mean square error type of laws, right? Then the neurons will be configured in a way that, it optimally compress the original input into some low dimensional embedding, and then, reconstruct the original signal. So here's one example of training autoencoder on a very simple, image data set. So this is called a MNIST handwritten digit data set. So somebody for some reason collected all kind of handwritten digits. Okay, so there are many different ways of writing 4, for example, and then they collected a database of all kind of 4s written by different people, different handwriting, and then the digits are, from 0 to 9, so total 10 different, digits. And then as you train the model like this, then the autoencoder should be able to reconstruct the original, image. And if you think about it, the original data set has 28 pixels across and 20 pixels vertically. So that's total of 84 pixels. 784 dimension sounds quite redundant, describing the shape of this handwritten 4, right? There's got to be a better way of representing the number, the style of writing. And then I think, you should be able to do that with a smaller set of, or to do it manually, then what would do is, I don't know, define something like the height of the digit, the width of the digit. So those are 2 parameters. And then maybe, let's say, the curvature over here, the 4. Some people love to have this stroke all the way up to here, whereas some people just stop over here and then just, draw this vertical line. So the length of that tail could also be another variable. So that's 4 variables. And then you can add more variables to describe the geometry of this handwritten 4, right? But likely you're not going to need all 784 dimensions. With much smaller set of numbers, you should be able to represent the geometry of this number 4, right? Oh, of course, if we do manually, then we may miss certain features, and that, definition of features may not be sufficient to reconstruct the original image. So that's why we're introducing a data-driven model, particularly a neural network. And the neural network will somehow learn to encode those geometric features into this d-dimensional space, so that using only D numbers, you can reconstruct the original image, is what's going on. So in this particular MLP architecture, the first half, okay, so we have a stack of 2 perceptrons. The first perceptron that reduces the dimension from N to D is called an encoder network. And then the second part of the perceptron, the one that reconstruct the D-dimensional embedding into N-dimensional original signal, is called a decoder. So we have an encoder and decoder, and then the word auto is basically we're encoding the same image and spitting out the same image. So it's called autoencoder. So the simplest form of autoencoder, like I just said, is a stack of perceptron, where each perceptron encodes the image into, so the image X gets encoded into P, the lower dimensional embedding. So that's what the encoder perceptron does. And the decoder perceptron will take P as an input and spit out the reconstructed version of X, which is X prime. And then once the reconstruction is done, we basically define a reconstruction error. So L1 norm is a mean absolute error, and L2 norm is a mean square error. So it's either of these two is the error. And from there, we basically train the model to minimize this reconstruction error. And then eventually we should be able to find the optimal W and an optimal, optimal W and B for both encoder and decoders. So that is the very basic type of autoencoder. And of course, it doesn't have to be a single perceptron for the encoder. So you can have actually multiple perceptrons on the encoder side and multiple perceptrons on the decoder side. That's totally fine. Now, one thing is, with deep learning, people have been utilizing convolutional neural networks, right? And convolutional neural networks are, generally more powerful than the usual MLP when it comes to image processing tasks. So we would like to introduce that for autoencoders. Okay, it's kind of the idea here. So with some number of convolutions, right, we encode the image, and we already talked about convolutional neural nets and how it works. So the encoder part of the convolutional neural network, convolutional autoencoder, is essentially just the usual convolutional neural network, right? You apply convolutions and pooling. Pooling is the downsizing, right? And then apply some convolution, downsize, apply convolution, downsize. And then at the end, you'll have much smaller dimensional representation of the original image. So that part works just fine. But then in terms of the decoder design, how do you do that? Because for the decoder, we somehow need to define the reverse process of pooling, reverse process of downsampling. Okay. And then also we have to somehow define the reverse process of convolution. But if you think about it, the forward convolution was the process of aggregating a group of pixels into a single value. The reverse process means you have to start from one value and somehow create a group of pixels. Okay, which sounds like a, not so straightforward thing to do. So this is where we introduced this thing called the transpose convolution. So here is a revisit of the convolution operator. The usual convolution, the forward convolution, we have an input image. And let's say we have a 3x3 convolution kernel. What happens is we slide that 3x3 kernel over the image. And each time we slide the image, we take the weighted sum of those 3x3 pixels to produce an output pixel. And then we slide the kernel again, compute the weighted sum of those 9 pixels, produce output, and so on and so forth. So that process, written in a kind of a dumb representation here, we have the input pixels, x0, 0, 0, 1, 0, 2, 0, 3, x1, 0, 1, 1, 1, 2, 1, 3, blah, blah, blah. So basically this, 4x4 pixel image, input image, we basically flatten this into a long vector for the purpose of illustrating what's going on. And then if you think about it, the weight of this 3x3 kernel, convolution kernel, is represented as W00, W01, W02, W10, 11, 12, 20, 21, 22, right? So we have 9 values. And those 9 values are multiplied in a particular manner, right? To produce the output, which in this case, we have 4 pixels. So Y00, Y01, Y10, Y11, those are the 4 pixels that we're producing as an output. And then, if you look at the geometry of, how the numbers are multiplied, this is the matrix representation of that multiplication you can see. All right. Now, consider the backpropagation process of this convolution layer. Why all of a sudden backpropagation? Because, by looking at the backpropagation, we're gonna actually deduce what's called a convolution, transposed convolution, which is kind of a reverse process of the original convolution. So backpropagation, what we're interested in computing is the gradient of the loss function, okay? Let's say this time with respect to the individual pixels, okay? So partial L, partial X 0, 0, partial L, partial X 0, 1, yada, 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 is what we're interested in computing. So basically the derivative of L with respect to this vector over here is the gradient that we're interested in computing. Now, that, by the chain rule, should be the gradient of L with respect to Y. Okay, so partial L, partial Y 0, 0, partial L, partial Y 0, 1, partial L, partial Y 1, 0, partial L, partial Y 1, 1. That's what's represented by partial L, partial Y, right? And by chain rule, that multiplied by partial Y, partial X is going to be the gradient that we're interested in finding. Now, partial Y, partial X, okay, is the derivative of Y with respect to X 0, 0, X 1, 0, X 2, 0, and so on and so forth. So if you look at how Y 0, 0, for example, is represented in terms of the X, okay, we know that the derivative of Y 0, 0 with respect to X 0, 0 is simply this coefficient W 0, 0. The partial Y 0, 0, partial X 0, 0 is going to be this guy over here. Similarly, partial Y 0, 0, partial X 0, 1 is going to be simply this guy over here, W 0, 1. And in the same way, we can basically calculate the Jacobian, partial Y, partial X. And if you do that calculation, you will realize the Jacobian is nothing more than the transpose of the original matrix over here. Okay. So if we call this entire thing a matrix C, then this guy over here is nothing more than the transpose of the original matrix C. Okay. And in fact, for backpropagation of a convolution layer, this is sort of what happens. Okay. You have the original convolution weight matrix. Okay. In the forward path, this gets multiplied by whatever the input is. During the back, however, we just compute the transpose of that guy and then multiply to the upstream gradient propagated back to the X side, right? Is what happens during the back propagation. And from there, we get the idea. When we go from, when we go from a 2x2 small image to a 4x4 large image, we can simply multiply the transpose of the convolution. And in that way, you can go from a 2x2 distribution of values, okay, to a 4x4 distribution of values, okay, using the transpose of the convolution layer. So basically, the idea of transposed convolution is to have of the transpose of the weight matrix, okay, and then multiply this transpose of the matrix as if this is the actual convolution kernel. Because in terms of the math, there's nothing there's nothing specific. We have some weight matrix, we have the input, and we just multiply that the weight matrix on the input. Same thing, after the transpose, we have the input, because in the back propagation, we go from the 2 by 2 to 4 by 4. So 2 by 2 is the input. And on that input, we just multiply this guy, which is simply a transpose. So this is nothing but the usual, multiplication of the convolution layer, convolution weights, but in a transposed manner. So the idea of transposed convolution is essentially that, and the operation itself is like the usual convolution. So it's still very efficient. Initially, when people first invented this method, they used to call it a deconvolution layer. That terminology is wrong because if you're a mathematician, deconvolution is something else. There's a thing called the deconvolution, which is quite different from this particular thing. So early papers, early research papers will refer to it as a deconvolution layer or deconvolutional neural network, but more correct terminology is either up convolution or transposed convolution. Some strange people use the term fractionally strided convolution or backward strided convolutions, but why, right? So it's either up convolution or transposed convolution is the correct terminology. And that's really it. And if you think about the way that these weights are multiplied, this is the animation showing that process, and you can see that transposed convolution is sort of similar to the convolution process where we have some zero paddings on the side. Okay, just looking at the geometry. Here's another perspective. So, in terms of the output, this output over here is the result of convolving this part of the input. And this output over here is the result of convolving this part of the input, and so on and so forth. So then when we go backward, we're basically redistributing this value to this 3 by 3 area, and then also redistribute this value onto this 3 by 3 area, and yada, yada, yada. And then at the end, you just add the 4 by 4 images together, and then you'll get the unconvolved or upconvolved set of features. Of course, when you have certain padding or strides in the forward convolution, you can pretty much find the transposed convolution that correspond to that. So transposed convolutions are uniquely determined given any arbitrary convolution with different padding and different strides. I guess I'm not going to go into the details, but roughly speaking, when you have a stride of more than 1 pixel, so the 3 by 3 kernel moves by 2 pixels as opposed to 1 pixel like in the previous case. And in that case, it is equivalent of the reverse process of that is equivalent of applying 3 by 3 convolution with some artificially padded pixels in the middle, okay, filled with zeros, and then apply convolution as usual. Here's some other example where we have now the zero padding added to the side, and then the stride is still 2 pixels. So in that case, this is the reverse process of this is equivalent of this. So it's all arithmetic. So I'm not going to really go into the details of how exactly you determine this. It's all arithmetic, so you should be able to figure this out on your own. But that's essentially what happens. So let me actually skip a few slides here. So deconvolutional neural networks. This is wrong terminology, but back then people didn't know. But the idea over here is the encoder part of the neural network. You basically do the same thing using the usual convolutions. And then you learn the convolutions over here. Take the transpose. That is your decoder. Okay. is kind of the idea. Now, that was about convolution. Of course, pooling is another operation that we need to somehow figure out. The reverse process of pooling is something that we have to figure out. So, you know, pooling is a downsampling process. So in the forward process, what happens is if you have a 4x4 image, for example, a 2x2 pooling is going to split this image into 2x2 patches, right? And for this 2x2 patch, what you're going to do is to select either the maximum value, which is called a max pooling, or compute the average of those 2x2 pixels, which is called average pooling. But the reverse process, it's not, really straightforward. So there are, a couple of different strategies. One is the nearest neighbor strategy. So although I call it a naive strategy, this is a very popular strategy. The nearest neighbor strategy, simply you double the size of the original input, and then basically just repeat the same value to fill out that 2x2 area. So this is the simplest way of defining up pooling. Or there's also a technique called the bed of nails, which is an idea of placing the numbers at the corner of each of the 2x2 tiles, 2x2 patches. And then the rest is just filled with zeros without introducing any repetition of pixel values. Of course, why over here? Why on this corner? Why not this corner over here, right? You may wonder. Well, because of that, some earlier works of convolutional autoencoders, they actually introduced a memory, an additional memory to the pooling layer, so that in the forward pooling, you memorize where the number came from. So let's say we have a max pooling, layer over here. And then from this 2x2 patch, we have 1, 2, 3, 5, and 5 is the largest number. So by max pooling, we get 5 downsample. And then same thing on this 2x2, we have 6, 3, 2, 1. So 6 is the largest number. 6 becomes the value after downsampling. So that's the max pooling process. And then when we do that, we remember where 6 has come from, where 5 has come from each of the patches. So that by the time you do the unpooling, you remember that position. And then whatever signal comes from the upstream, we're going to place that number at that exact location. Is kind of the idea of max unpooling. So in 2000, in between 2004 to 2014 to 2018-ish, people have been experimenting with a lot of different, unpooling strategies and, up convolution strategies. Okay, so what we just saw is, is a few of those. Like this one over here is one of the earliest work, which is called the fully convolutional networks. And these guys haven't figured out the up convolution process and the unpooling process. So what happens over here is you have a forward convolutional neural network, reduce the dimension up to, some 21 dimensional, encoding. And then from there, just directly using multi-layer perceptron, you just expand the number of pixels, okay? So that you can, reconstruct the original signal, or in this case, generate what's called a segmentation map, assigning, labels for individual pixels. So this pixel over here looks like a dog. This pixel over here looks like a cat. So you're basically assigning numbers, corresponding to different class. And then they solved the problem in this manner because they couldn't figure out the reverse process of convolution and the reverse process of pooling. But then here is one of the first works that has figured out how to, do the reverse process of convolution and pooling, and they named it as a deconvolutional neural network. But then later, people chimed in and said, "Oh, the term deconvolution is inaccurate because there's a thing called a deconvolution in mathematics, and it's not the same process as what they're presenting here." Yeah, so in that deconvolution neural network, they actually use this bed of nail technique, where you memorize the location of where the pooled value come from, and then use the unpooling based off of that. So here is a really nice illustration of the whole process. So you have the original image, and then through forward convolution, this is the feature map after the dimension reduction. Okay, so you can see that the pixel resolution is much sparse, and the numbers somehow encode this scene into some values, right, in this low resolution representation. Now after unpooling, this is what we get, and we have this bed of nail technique. So out of this blank image, we have some scattered distribution of pixels unpooled from here. Okay, and then because they remembered where the originally pooled value come from, the nails are not regularly distributed. Now from there, they apply transpose convolution, and the role of transpose convolution, as you can see, is to fill in the blanks, right, by referring to the other neighboring pixels. So now you have a smooth map like this, and then followed by the bed of nail technique again. So unpull, and then transpose convolution, unpull, transpose convolution, unpull, and then you keep adding resolution, more details, and then eventually you have the probability distribution showing which pixel belongs to bicycle and which pixel belongs to the background. Okay. There's some other examples. So here, again, using the deconvolutional neural network, we have a probability map showing which pixel belongs to a puppy and which pixel belongs to the background. Same thing, here's a bicyclist, and then we're interested in the bicycle itself, not the human. So the pixels that belong to the bicycle will be highlighted, whereas pixels belong to the background or the person will not be highlighted. So this is kind of how the thoughts were. I mean, the initial kind of a pioneering thoughts in this whole idea of convolutional autoencoders. This is another thing called the SegNet. SegNet was published in the same time, same year. And by coincidence, they look very similar. Okay? They look very similar to each other. Both were published in 2014, and that was a time where like everybody was publishing something about deep learning. And by coincidence, I don't think they sort of cheated or anything, but by coincidence, they sort of presented the same, almost the same architecture. They at least didn't use the term deconvolution, so I give them credit for that. But essentially the same thing. You have a bunch of convolutions followed by pooling, convolutions, pooling, convolutions, pooling. So that's how you define the encoder of the encoder part of the convolutional autoencoder, right? And then from there you have upsampling, and then the arrows basically indicate the memory of the pooling indices. So where the pooled data come from, it's stored. So it's almost exactly the same, right? So we do the upsampling or unpooling, followed by transpose convolutions, and then so on and so forth. Oh, sorry. One actually a key difference between the deconvolutional neural network and the SegNet is that they actually don't use the transpose convolution. They just use the regular convolution. So only thing that introduced is the upsampling with the pooling indices. Nonetheless, so those were the early, kind of convolutional autoencoders. Okay. And that was the breakthroughs in the 2014. And then in 2015, we have this this thing called the U-Net. And U-Net, probably many people in the audience may already know what U-Net is, because U-Net is one of the most popular architectures in medical imaging, but also in other applications. U-Net is pretty widely used. So diffusion, generative diffusion models, for example, the synthetic image generation algorithms in the backbone, they actually use the U-Net architecture. So U-Net is a very versatile, very popular architecture that a lot of people are using for a lot of different applications. The idea of U-Net is very similar to the SegNet architecture. So we start from an input image, okay, apply convolution, and then apply pooling to downsample to a lower dimensional image. And then, repeat the same process again, convolution, pooling, convolution, pooling, convolution, pooling, convolution. So that's forward path, encoder path. The decoder path is the same as the previous, SegNet architecture. So we do the up convolution, up convolution, and then followed by the regular convolution. We do the up convolution and then regular convolution. So the up convolution, instead of the unpooling, is what's being used over here. And that up convolution is essentially the transpose convolution that we saw, right? So the transpose convolution allows you to go from the low resolution image to a higher resolution image, and then they apply the regular convolution to further develop the features, right? And then by repeating that, you reconstruct all the way up original resolution, right? And then that's how U-Net produces an output. Now, a very unique feature. So, if you just look at that part, it's pretty much the hybrid of the SegNet architecture and the deconvolutional network architecture. But the uniqueness, the main contribution of U-Net comes from this gray arrows. The gray arrows are essentially the copy operation of the original format. So on this side of the encoder side of the U-Net, we have convolution, and then as a result of those consecutive convolutions, we have a feature map developed. That feature map is copied, okay, in the decoder part of the neural network. And that copy operation happens at every tier in this U-Net architecture. So right before you do the pooling, you make a copy, you create a copy of the feature map. So we have a copy of this guy, we have a copy of this guy, we have a copy of this guy, and this guy. And these copies are concatenated after the up convolution so that the up convolved features are combined with the encoder features before it undergoes 2 consecutive convolutions to develop features. And then each time we go through the up convolution, we do the concatenation, and then convolve, up convolution, concatenate, convolve, and eventually that's how you generate an output map. Okay. By having this copy operation, what U-Net achieves is a high resolution. So if you go back to the previous example, you will see that the reconstructed results are good, but there are kind of blocky and round. And that's because during this process of going down to a low resolution and then go back up to the higher resolution, you get to lose all the details, right? And for some applications, details are the ones that are actually important, like in medical imaging. So UNet was first published in a conference called the MICI. That's the best conference in medical imaging. Even harder to get in than many of the journals actually. So the acceptance rate is really low. But the UNet paper was first introduced in that medical imaging conference, because in medical imaging applications, you want to be able to delineate all the all the details, right? You cannot just say that roughly this round blob is a cell, but you want to have an exact delineation of the boundary. And the authors, Roneberger et al., didn't like the fact that the existing convolutional autoencoders ignore all the details, the reconstruction process, and they lose all the details. So they introduced the UNet, and then demonstrated that their algorithm were actually able to achieve all the details after the segmentation. So that is kind of a brief history of convolutional autoencoders. UNet onwards, we don't seem to see a lot of breakthroughs. A lot of convolutional autoencoder architectures that were published after UNet are some variation, some variant of the existing method. So which is why I'm not talking about those other variants. So there are things like VNet, which is a slight a variation of a UNet. There's all kind of variants of UNet with different tweaks, but as long as you understand how UNet works, probably you should be able to do pretty much what you'd like. Any questions? Yes. Mhm. That's a great question. Many of those autoencoder methods do not allow the users to make that kind of intervention. So many of them are actually purely data driven. I guess you could let the user to make an intervention. I actually never thought of it that way, but for physics applications, let's say you're interested in some turbulent behavior in fluid simulations, and for those kind of simulations, what you weigh more are the the turbulent patterns, the vorticity patterns, and those patterns than what's happening in the ambient space, right? So during the reconstruction, you may want to put more weight on those particular features compared to the other features in the ambient space. Maybe you could do it with some sort of a loss function, where in the loss function, instead of equally weighting pixels, you could calculate things like the gradient to differentially weight different pixels. So the pixels with the high gradient will be weighted more, and pixels with the low gradient will be weighted less. So in that way, those violent patterns will be weighted more, and then the boring flow on the ambient space is going to be weighted less, right? And there are actually some papers that introduce that kind of idea, but in the context of autoencoders or dimensionality reduction, I don't think I've seen any of those. So yeah, that's actually an interesting point. Hmm. Yeah, yeah. Mm, 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 mm. Sure, sure. Yeah. No, I don't think there's a method that's readily available for that. Although I think, by introducing, something like what I explained in the loss function side, or, if it is simply the frequency of the signal, then you could introduce, free, you know, neural network layers to kind of filter out the high frequency components. So I think there could be many different ways of achieving the goal, but I'm not aware of a readily available method for that. Yeah, that's a great question. Any other questions? All right. Um, so that's about the design of the architecture, and then in terms of the actual training of the autoencoders, um, almost all the time for the training of autoencoders, you will need some kind of a noise because autoencoders are quite easy to overfit. And most importantly, autoencoders do not really guarantee the continuity of the mapping. So if you just let it train in a naive manner, you will end up creating a map where Mexico is next to India, um, China is right next to the U.S., Brazil is on the top of U.S., and all this kind of crazy um, you know allocation of so it'll not have any guarantee in terms of the continuity of the map. Okay, the map may very well look like mosaic of different parts and different continents, different countries stitched together in a weird manner. Um, so a simple way of overcoming that kind of limitation is by introducing some noise during the training and sort of an uncertainty. Okay. So you're basically saying that, oh, Brazil might be, below US, but I'm not going to tell you exactly where, how far below US on the map. And by injecting those kind of uncertainties, you're making the neural network to converge to, more continuous mapping. Okay, is kind of the high level idea. So in that regard, there's a thing called the denoising autoencoder. The idea of denoising autoencoder is you intentionally corrupt the data by introducing noise. So for example, instead of giving this as an input, you basically give a corrupted version of that. So in computer vision, it's called a salt and pepper noise. So you basically create a random set of white pixels and create a random set of black pixels, and then corrupt the input so that image of 7 now looks like a weird, almost like a TV static, right? But the structure of 7 is kind of there; it's not completely gone, right? So for each training iteration, for each epoch, what you do is to create a random noise like this, and then train the model using that noise input. The goal of reconstruction is still this. So in the ground truth, we're going to present the clean ground truth without the noise. But on the input side, we're basically, adding noise like this. And then by doing that, it is known that autoencoders trained in this way are more robust, less overfitted, and then the encoding space tend to be more smooth and continuous. Of course, the uncertainty can be added not only in the input node, but also anywhere in the middle. So the idea of variational autoencoder is to introduce the noise not on the input side, but on the latent encoded vector. Okay, so the variational autoencoder first encode the original image, okay, using a convolutional neural network. But this convolutional neural network, instead of encoding the numbers directly, will actually produce two outputs. One output is called a mean vector. The other output is called a standard deviation vector. And from the mean vector and the standard deviation vector produced by the convolutional encoder, we are going to sample a random, okay, latent vector. And again, the random latent vector each time changes, right, during the training iteration. So even for the same mean and the same standard deviation, you can have different set of latent vectors, the encoding vector. So you let the encoder to predict the mean and the standard deviation, but from random sampling, you sample an encoding, of the original image. And from that randomly sampled encoding, we then apply the decoder convolutional neural network. And then the decoder network is going to try to reconstruct the original image. And that is the idea of variational autoencoder, which is very, very popular in the autoencoder community. So using this variational autoencoder, here we're going to see an example. Okay. In fact, there are many ways of reducing the dimensionality of physics and, learn physics in the reduced dimensional space. But this is still kind of an, active area of research, and there's no single method that is perceived to be a state of the art or anything. But people somehow introduce variational autoencoders to solve their problem. So here's one of such applications of variational autoencoders on that energetic material example. So in this particular problem, the goal is to learn the underlying dynamics of three fields. One is a temperature field, and the second is a pressure field. And then we are also interested in the deformation of the geometry. So the microstructure mu is the third field that we're interested in modeling the dynamics of. Okay. And then what we are hoping to do is to somehow use the variational autoencoder to encode the temperature, encode the pressure, encode the microstructure into some low dimensional representation. And we're going to use variational autoencoder, which means we're going to have a mean and a variance, okay, for each of those. So ZT is the latent encoding, low dimensional encoding, reduced dimensional representation of the temperature. And then we have the ZT bar, which is the mean of that. And then ZT sigma, which is the standard deviation of the encoded temperature. We do the same thing for the pressure. So ZP is the lower dimensional representation of the original pressure field. And then again, we have two things, ZP bar and ZP sigma. ZP bar is the mean, ZP sigma is the standard deviation. And lastly, we do the same thing for the microstructure. So Z mu is the latent reduced order representation of the microstructure field. And then bar denotes the mean, the sigma denotes the standard deviation. So here's kind of a sanity check. Okay, so we have an evolving pattern of temperature field, and then using variational autoencoder, we encode this into some low dimensional representation. And then from that low dimensional representation, we reconstruct the original temperature field using the decoder convolutional neural net. So the top row is the ground truth, and then the bottom row is the reconstruction result of a variational autoencoder. And you can see virtually no difference between the two in terms of the reconstruction quality, despite the fact that the compression ratio is 64 times, I believe. Okay, so we have a 64 times smaller dimension to encode the physics. So 1/64th of the original dimension. But still, we're able to preserve pretty much all the details, with the caveat that the reconstructed field may look a little blurry in some locations. So if you look at this image really close, then you will see that the boundary between two temperature regions are a little blurry compared to the original, but maybe we can leave with it. Now, the bottom two rows are the actual z's. Okay, so we have the representation of zt, and so we have a zt bar and a zt sigma. Zt for each pixel, we have 4 values. Okay, and then what's displayed over here is one of those 4 values. And as you can see over here, z bar t, the mean field, somehow encode the original temperature field into some distribution of numbers. And it seems like this particular ZT is encoding not only the location of the hotspots, but also the traveling shock is somehow encoded. Okay, so the shock front, as it progressed, the shape of the shock front is somehow encoded in the ZT bar. And then ZT sigma is the standard deviation of the ZT in a normalized log scale. So that's why we have the negative values for the standard deviation. But in that log scale, we have something like this. And, that's basically the visual representation of the encoded temperature field. Same thing goes with the pressure field. So as you can see on the top, we have the ground truth pressure field. And then in the bottom, we have the VAE reconstruction. Again, we are encoding the original pressure field into a lower dimensional space. And that lower dimensional representation is used to reconstruct the original pressure field. And then you can see that the reconstructed version versus the original pressure field, there's virtually no difference. Okay, so it's a very good reconstruction result. And then we have the example of the Z field. So ZP over here seems to be capturing a bunch of different things. This one is a little harder to interpret, but it seems like it seems to be capturing the shock front again. But then I think there's a lot more going on. And in terms of the interpretability, it is not terribly interpretable. So some, interesting geometric pattern is created as a result of encoding this, but exactly what that is still kind of a question. The third one, the last one, is the microstructure field. So as the shock hits this microstructure, this thing will collapse and then kind of shrink like that, right? And that process was encoded by the variational autoencoder. So for each snapshot, we have the encoding and reconstruction. And then the reconstructed result is, again, pretty good, right? And then automatically there was a little bit of noise filtering. So in the original ground truth, there was a little spiky, surface, whereas the reconstructed result is a little blurry. But because of the blurriness, now the microstructure geometry looks a little smoother. So there's that. And then here, obviously, Z mu is capturing the boundary of the microstructure. So we have this, this encoding for Z mu with the mean and the standard deviation. Okay. So these are the low dimensional representation of the original dynamics that is being used to reconstruct the original dynamics. So far, the 3 slides that I just presented is simply the reduction of the dimension. But how do we learn the dynamics over there, right? Is now the question. So the key idea is, well, here's another, visualization of what's going on. I move on to the next. So, the dynamic starts from here. And then this is when the shock arrives. The shock hits the pore. And then because of that impact, there's a change in the dynamic trajectory. And then this is after the pore collapse. When the pore collapse is over. This is in the middle of the pore collapse. And then this is when the pore collapse ends. And then boom, high temperature started developing. Okay, so how do we learn the dynamics now that we have the reduced dimensional encoding? So here we introduce this capital F, okay, as an operator that defines the dynamics in the latent space, okay? So in that reduced dimensional space, in the space of Z's, as opposed to the original TP and mu, we have now the Z bar T, Z bar P, Z bar mu stacked up together to represent the state in the latent space, okay? And we're interested in the evolution of Z bar T, Z bar P, Z bar mu over time. And F bar is an operator, okay, that takes a state as an input and spit out a new state as an output. And then we define that for both the mean Z and the standard deviation of Z, okay? And we call it the upper part, the deterministic part of latent dynamics. And then the lower part, we call it the stochastic part of the latent dynamics, okay? So Z bar and Z sigma are both evolving, and we're interested in learning the operator F bar and F sigma describing that evolution. And of course, we model F bar and F sigma as a neural network module. More precisely, this is a small convolutional neural network with a few convolution layers. Assuming that in the lower dimensional space, the dynamics, becomes more much simpler. The hypothesis here is that a relatively small convolutional neural network should be able to learn the dynamics. So there's a lot going on, but in terms of what's happening, we have the temperature encoder, pressure encoder, and the microstructure encoder. And each of the encoder will spit out the mean and the standard deviation of the latent representation. And then those basically go into F bar and F sigma. And then the F bar and F sigma will produce the prediction of the updated Z, T, ZP, and Z mu, right? The new state. And then from there, we have the decoder for T, decoder for P, decoder for mu. And then at the end, we have the reconstructed TP and mu after time delta T. The training of this, okay. Oh, sorry. Yes, so the coupling, across the 3 field is learned by F bar. Yeah. So the variation autoencoder was trained separately. So the T encoder only encodes T, and there's nothing about the pressure or microstructure. And same thing goes with the P encoder and the mu encoder. But then they get coupled by the dynamics, okay, is what's going on. Good question. Other questions? All right. So for the training of this guy, we have multiple loss functions, okay? First, we want the predicted temperature field, predicted pressure field, and the predicted microstructure field to be as close as possible to the ground truth. So that is the dynamics prediction loss. But also, if we have the ground truth at time I plus 1, and then encode that ground truth using the autoencoder, then we'll have a ZT I plus 1 encoded from the ground truth. But then we could also think of a path where we start from a temperature at I, encode it, and then using F bar predict the Z at I plus 1, right? So those two different Z's, we want them to be the same, right? So that is another loss function that is introduced for the training of this guy. And then basically using those two, loss functions, okay, we want the prediction, the reconstructed temperature, pressure, microstructure to be the same, and also the predicted E to be consistent with the encoded Z, right? Using those two as the loss function, we train this model. And then as a result of that, this is kind of, what we get as a result. So the first column is a sample that was included in the training data set. So the model has seen this already. The second column and the third column, on the other hand, are the test samples. Those are set aside during the training, so the model has never seen. And when we apply the model to those samples, this is what we get. There are a few things that we can notice from here. Is that the global pattern of the hotspot formation is captured by the dynamics model. But then you will notice that the prediction result is somehow blurry. Yeah. So this is a kind of an inherent problem with autoencoders, because we're reducing, compressing the dimension. So like when you have a video or a selfie, if you compress your image too hard, then after the reconstruction you will see artifacts. So this is almost inevitable in the reduced order modeling. But also the variational autoencoder itself, we have the stochasticity. So because of the standard deviation, the stochastic part over here, as we roll out the prediction, the stochasticity will grow. And at the beginning, actually, the details are there, relatively speaking. But then as you go further in time, the prediction becomes blurrier, blurrier, blurrier. But with that caveat, you can see that the predicted temperature field is pretty close to the original dynamics, despite the fact that we're learning the dynamics in a space where the dimension is only 1/64th of the original dimension. Here's the pressure field. So that blurriness becomes more prominent in the pressure field prediction. So again, on the left, we have the training sample. So this is something that the model has seen already. And then the second and the third, we have the test samples. Those are the samples that the model has never seen. And as you can see, the overall pattern is there, but the exact sharp boundary of the shop front is kind of blurred out in the prediction. Here is another view. So now we have the predicted temperature. So this is not the VAE reconstruction, but the predicted dynamics in the reduced order model. And then for that predicted dynamics, this is the evolution of the Z field. that is predicted by that F, the dynamics model. And as you can see, you know, some evolution in the Z field is captured by that F, from which we can reconstruct the original temperature field. That's that. For the pressure field, we get the same thing. One funny thing is that there's a blob, even though in the pressure field after the evolution, it's all kind of, constant pressure everywhere. And that is because we believe that the dynamics is sort of coupling the role of pressure in the formation of temperature and vice versa. And somehow I think the dynamics of Z bar and ZP sigma are capturing those little blobs, because we have to predict the evolution of the temperature and so on and so forth. But I think there's a room for further investigation. So this is kind of the the key idea of reduced order modeling. Okay, so you use things like autoencoder, reduce the dimensionality, and create a map, right, on a lower dimensional space. And on that lower dimensional space, you basically model the dynamics, and then basically make the predictions in that lower dimensional space, and then later on reconstruct the original dynamics. Is kind of the idea of reduced order modeling in the context of deep neural network. Now, the real interesting part in this work is actually the idea of scale bridging. So in a lot of mechanical simulations and a lot of physics phenomena, actually there are a lot of different things happening at different scale. So at a micro scale with a single pore, all this kind of weird patterns emerge as the temperature and the pressure evolve. But then if you kind of zoom out, right, and go to the mesoscale, where now you have a collection of those voids, right, in the microstructure, then as a combination of those single void phenomena, now you have much more sophisticated pattern like this. Now, the idea of scale bridging is to, find the dynamics describing these two different scales, okay, and then find some mathematical relationship between the two. In other words, if this is the single void phenomena, and we just saw that in the previous slide, we just saw that we can model it using reduced representation. So we have a bunch of Z's, right, to represent the single void phenomena. Then we should be able to combine those Z's to describe this larger structure, and then describe the dynamics using those Z's. Okay, so if I were to use the natural language analogy, single void is like one word, and for each of the word, we just learn how to encode that into a numerical vector Z, right? And for each word, we were able to make predictions in terms of what the pressure field look like. Now, if we go to the larger structure, then we have a collection of words, which is equivalent to a paragraph, right? Now we have a collection of words in a particular, arrangement, right? So we have a paragraph. Now, if we know the meanings of the word, can we predict the meanings of the paragraph? Is kind of what's going on. So this is, again, an area of ongoing research. So there's a lot, of new methods. I mean, not a lot of methods for this kind of problem, but here's what we were able to do in very recently. So we are interested in learning the mesoscale dynamics, okay, as a combination of the microscale dynamics. And here is the result where, we simply just place different Z's from the autoencoder, okay, based off of the local geometry of the structure. And then based on those Z's, we simply just predict the temperature evolution using the Z's that were learned from the single void simulation cases. And as you can see, they're kind of off, okay? They're kind of off compared to the ground truth. They do seem to have the right location of the temperature hotspots, but the shock front moved much faster, and then the growth rate of the temperature, the hotspot is not the same. And what we guess here is when you have only single void, then there's no other voids interfering the development of the dynamics. So you have almost like a freeway, except for that single void where the dynamics can evolve. So once you hit the void collapses, develop the heat. Afterwards, there's a freeway, there's a highway where the dynamics can progress. And the model that has not seen the multi-void scenarios, it just assumes that after the heat is formed, it could just travel at a speed where there's nothing else on the way. Versus in reality, because we have voids after voids, they kind of interfere, right? The progression is actually much slower. And then you should also, consider the coupling, right? The heat generated by this guy and the heat generated by that guy, they couple, sometimes, amplify and enforce each other, sometimes kind of cancel out, right? That kind of dynamics needs to be considered, but obviously that's not there. But after we fine tune that F bar and F sigma on the mesoscale data, this is kind of the training result that we could find. Now the model has learned the mesoscale interaction between pores, and then the prediction of the hot spots and things like that are much more accurate. So here's the animation. Again, we have the training sample. So this is the case that the model has already seen, and then we have two test scenarios that the model has never seen. And as you can see, again, with the caveat that the prediction result is a little blurrier at the bottom, we can capture the overall dynamics of the hotspot formation and then their coupling as well. Here's the pressure field evolution, same deal. We have some, noise, blurriness, and then you can see a little bit of noise. That's coming from the stochasticity, the sigma, and the sigma adds uncertainty. So we get to see this kind of weird blobs popping up here and there. But other than that, you can see that the general pattern of the traveling shock front is correctly modeled. So the benefit of this kind of scale bridging is that, in case of, simulation, the single void simulation is a lot less expensive compared to the larger scale simulation for an obvious reason, right? So if you have a smaller scale that you want to simulate, that's, much less expensive compared to a larger grid. So, we can afford a large number of single void simulation, relatively speaking. Whereas for the large scale simulations are way much more expensive. So if we wanted to predict the large scale simulation with a small, number of samples, then training a neural network is going to be, pretty sophisticated. Instead, Alternative strategy, now that we know how to bridge the scales, alternative strategy would be to, train the model with lots of single voice simulations. And for single voice simulations, again, they're less expensive. So we can afford a large number of data, train the model over here, and then with a few large scale simulation, you fine tune the model. And in that way, you can save some simulation time, is kind of the idea. So what's described as red and purple line are the ones that are based off of the scale bridging. Whereas when you try to train a model with only the large scale simulation, this is kind of the training curve. And as you can see, the ones that are pre-trained using the single void simulations, and then later on, transfer to the large void simulations, are actually, much faster in terms of the convergence of the training, whereas the ones that are, directly trained on the large scale simulation, we have much slower convergence. So only with one sample, for example, only with one sample we could, capture the ground truth quite well. I mean, not that accurate. With the 3 samples, the accuracy goes much, higher. And with 10 samples up here, we get, pretty decent prediction results, right? Because the model has already been trained on the, single void simulations. So it knows, the overall dynamics pretty much. It just needs to learn to connect the scales, and, using the small number of samples, we can teach the model to connect, bridge the scale. Versus if you train the model from the scratch, here with only one example, one large scale, sample, since the model does not know the actual dynamics, it kind of fails to predict the formation of the hotspots, very well. Of course, as we increase the number of samples, the prediction results get better. But in terms of, comparing to this, the ones that are pre-trained on the single void simulations tend to learn much faster what's happening in the larger scale, where, compared to this one that has never seen the single void simulation results. Yes. Correct. Hmm. So that's a great question. So for this particular example, we're actually relying on Eulerian simulation, and the grid size is actually uniform across the space. If we have an irregular grid, however, we're going to need to introduce things like graph convolutional neural networks. But that's something that, I'm not. That's something that I'm not trying to include in this, short course. But graph convolutional neural nets are actually, another kind of fascinating topic that has a lot of connection to them. Because, in real world, nobody uses a regular grid. It's always some sort of an adaptive grid, and your neural network should be able to incorporate those adaptive grids. But for the scope of this course, we're not talking about that. Yep. Other questions? So same type of deal for the pressure field prediction. So when you have only one sample, this is the result that you're getting, and then after 10 samples, again, to be fair, the pressure field is kind of blurry, so I don't know if this prediction result is good enough. But yeah, And as a matter of fact, in this case, the full resolution model trained directly on the large scale simulation, after 10 samples, actually tend to develop a better, more crisp, shop boundary, the shop front. But um, but yeah, I guess that's kind of the inherent trade-off between full resolution model and the low resolution model. And then the added benefit of this formulation, where we have not only the deterministic dynamics, but also the stochastic dynamics, is that the stochastic part of the dynamics naturally gives you the uncertainty of the prediction. So the standard deviation predicted by the dynamics model naturally translates to the uncertainty of the model, right? So the red areas are where the model is more certain about, more uncertain about, and then the blue areas are where the model is more certain about. So like for here, for example, the model is almost certain that there's nothing happening. But then near the hotspots, some of the hotspots are brighter red, some of the hotspots are kind of yellow, green. The red hotspots are the ones that the model is uncertain about. Right? So we can kind of graphically visualize this kind of uncertainty with that formulation. So far, so good. Yeah, no worries. Here's a few other method that I would like to introduce. So this is work done by a group at the Lawrence Livermore National Lab called the Latent Space Dynamics Identification, or LASTI. Pretty much the same in the sense that we have the autoencoder to reduce the dimensionality, but the favorite part of this idea is that when they identify the dynamics in the latent space, they actually introduce a lot more interesting ideas compared to what I presented in a few slides ago. So in their case, we have training data that are concatenated. So it's not a convolutional autoencoder; it's kind of flattened vector. Okay, describing the dynamics. And for each snapshot, we're using autoencoder to encode that flattened vector into a low dimensional representation. And in that low dimensional representation, there's got to be the dynamics, right? There's going to be the evolution of the trajectory. So for the dynamics identification, what happens over there is, first of all, you would like to have the reconstructed dynamics to be the same as the original dynamic, but also in the how do I say, in the latent space, they actually introduced a more analytic regression model. So as opposed to the previous case where we just threw everything into a neural network, they a regression model in the latent space to parametrically represent the trajectory of the latent space dynamics. And then from there, they basically identify the dynamic trajectory in the latent space, and that's basically what's being used for the prediction of in the full scale. And then here's a slightly advanced version of LASTI called the GLASTI. Again, the same group of people from Lawrence Livermore. This is actually a really interesting idea where we have the encoder that encodes the snapshot of the dynamics, and then we have the Z representation, the Z space representation of the original dynamics. But then they introduce automatic differentiation. Okay, this is something that we saw in the PIN lecture. And the automatic differentiation of the encoder is going to be the Jacobian of the encoder. And that Jacobian of the encoder is going to take the velocity of the dynamics. So now we have u dot, which is the time derivative, taking that, time derivative of the dynamics. This Jacobian is going to produce the z dot, okay, the rate of change in z space. And then from that z dot, we have the, Jacobian of the decoder, okay, from the automatic differentiation. And then that Jacobian of the decoder is going to take the z dot and reconstruct the velocity field, okay? And then there we have different loss terms. One is the reconstruction loss. So the reconstructed, fields should be the same as the original field is what the reconstruction loss is about. So this is the usual, the usual reconstruction loss in the autoencoder literature. But then there's this dynamics identification loss terms where the z dot, okay, computed by the Jacobian of the encoder gets compared against the z dots predicted by the dynamics model from the previous z values. Okay, so this psi underscore di is the dynamics module. So this is actually where things become pretty similar to Park, where right you have the current state in the latent representation that goes into psi, and the psi will return the z dot, the velocity, the rate of change, and that gets compared against the Jacobian computed the z dots, and then that is the first part of the dynamics identification loss. The second part of the dynamics identification loss is directly comparing the u dots, right? So u dot computed directly from the the original field, so the velocity field computed directly from the original physics, versus the velocity field reconstructed by the Jacobians of the autoencoder, right? And then that needs to be the same is the second part of the dynamics identification loss. And in that way, they were able to achieve a pretty good, latent dynamics model. And that was the whole, idea of GLASTI and LASTI. So for those of you who are interested in this, there's a link to the paper. So I encourage you to check out the publication. And this is kind of the direction that we're evolving towards. So you will notice that this is sort of like the Park in the latent space, right? In the sense that you first encode everything into the Z space, and then over there we have the differentiator. So this is, what's equivalent to the differentiator in Park that predicts the Z dot, right? And then we're just, basically evolving the dynamics using the differentiator. And then in between we have the autoencoder. So encode the vector, encode the physics to a lower dimensional space and then decode it eventually. So this is kind of a latent version of, I guess, Park in some sense. So with that, we'll take the break for 30 minutes. And then after the break, we're going to talk a little bit about generative AI. So last time, Professor Kana and Tandon mentioned that because of the, some conflicts, we're going to, tomorrow is going to be much shorter in terms of the technical lecture. So we're going to cover a little bit of generative AI today after the break. And then the remaining generative AI lecture will be covered tomorrow. So thanks and see you in 30 minutes. Welcome back.